All right, well, welcome to another Monday here in Calculus World. Hopefully your weekend was good. Before we get going, just going to let you know that the quizzes are not done. Still have somebody who's going to take it. So I'll have those hopefully posted for you either tonight or tomorrow. And we'll go over it on Wednesday. But as always, let's go ahead and start with any homework questions. I know, Fenru, you were about to ask one. Which homework problem would you like to look at?
In fact, I have like 3 questions.
Okay.
For the exercise 2.5, the number 9, 10, and 11.
Okay. We'll go at least look at a couple of those. Other homework questions people have? We can make our list and then go look at the Canvas. Excuse me. Okay, well then we'll go ahead and go take a look at those. So I will share my screen and then we'll go see if we can tackle some of those homework problems. Okay, so hopefully everybody can see my screen and we'll go pop in here to exercise 2.5. All right, so 9 through 11. Let's go take a look at what those guys are real quick. All right, so number 9, we're trying to find a delta. Same thing with number 10. Okay, so
the number 11, I don't know, like fx and a and l, but other I know.
Okay, well let's do this. Let's go back and let's start with number 10, I think. Okay, so when it says visit this Desmos link, we don't necessarily need to do that, but let's just see what this is asking us to do. So it says we want to determine a delta so that if absolute value of x minus a is less than delta, then f of x minus l is less than epsilon. So remember, our goal here is to figure out how close we need to be to the value that we're plugging in so that our function values are all within the same, are all within, excuse me, a certain distance of our function itself. Okay, and that's what this is. So you see that epsilon equals 0.001. That's telling us how close we have to be to the function value. So basically, we're going to figure out what the function value is at this point and then go up and down that much. So think about this. If we're going to approach 2, then this function is going to approach 5, it looks like, right? 3 times 2 is 6, minus 1 is 5. So we're going to want to be within 0.001 of 5. And so the question is, what kind of deltas will let us do that? Okay, well, I'm not gonna go to Desmos. I'm actually just gonna do this. So let me get a whiteboard screen up here. And let me show you how we can approach this. So here was our function. We had f of x equals 3x minus 1. Right? And we're looking at the limit as x approaches 2. Okay, so we plug that in, 3 times 2 minus 1, looks like it's 5. So what we want then is we want to figure out what x's make it so that we're between 5.001 and 4.999. And where those are coming from, because we had an epsilon of 0.001. So this was just 5 plus epsilon, and this was 5 minus epsilon. So you may remember that when we first did this with the definition, it was 5x minus L is less than epsilon, or sorry, f of x. So this is f of x minus 5 is less than 0.001. And if you were to take this inequality, make it a compound inequality, it would be this one in pink. So both of those mean exactly the same thing, okay? This statement and this statement, they're identical. They're exactly the same thing. And I wanted to show you it this way to remind you about how the epsilon delta stuff looks. But in a practical way, sometimes this is a little bit easier just to think of it as we're going up and down, whatever epsilon is. Okay, now, if we take it as I have it written down at the bottom here, and we put in our 3x minus 1, that was our f of x, right? 3x minus 1. What I'm going to do is I'm going to manipulate this thing until I get absolute value of x minus 2. So I'm going to factor out a 3. So we're left with the absolute value of x minus 2 is less than epsilon over 3. And the other part of the definition, oops, that's not where the delta goes. Right, the other part of the definition looked like this. Well, A, that's the point where we're approaching. So this is x minus 2. And so what we can do now is just go, okay, well, delta then is going to be epsilon over 3 because these two forms are identical, right? They're exactly the same. So what's on the other side of the absolute value, those things have to be equal. So what we've just seen, without a graph or anything, is that if you want to get a delta, given an epsilon, all you have to do is take that epsilon and divide by 3. So no matter how close you told me to get, right? This one told me, well, epsilon is 0.001. So what I'm going to do is I'm going to take that 0.001 and divide by 3. And I believe it gives me 0.00033333333 forever. So in terms of a delta I can pick, I can actually take any delta smaller than this or smaller. So this is the biggest possible delta. I can always go smaller. We can always shrink that down, shrink that interval down. But there's our delta. Now, if we were doing this with a graph, basically what I would do, actually, let me go ahead and show you what I would do there. But before I run over to the graph, any questions on what I did here? And the process is always the same. It's always start with f of x minus L is less than epsilon. Put in your L value, right? Put in your function, and then slowly make it look like absolute value of x minus a is less than delta. I think I wrote it as x minus c in class, but c, a doesn't really matter, right? Okay, so let's actually go to the link so I can show you what I would do graphically. So we'll go visit the Desmos link. All right, so it's usually this point in class when when we're waiting for things to upload that I ask people if they have any really, really bad jokes. And I mean bad like not like raunchy bad. I mean like groaner bad. For example, of course. So here's some of my favorites. Here's a math joke for you. What did 0 say to 8?
Why did you eat 9?
Oh, that's a good question. That's a good guess, but that's not right. Okay, so what did 0 say to 8? Nice belt. Think about it for a second. All right. So clearly it's not wanting me to open this link, so never mind. But basically what I was going to say is you could just zoom in. You could y bounds on your graph to be between 4.999 and 5.001, and you can keep zooming in until all of the graph that you see lies within that strip. Actually, let's try this. Let's see if it was really my open math that was the problem and not Desmos, because it looks like I'm able to get Desmos here the old-fashioned way. All right, so our function was 3x minus 1. So you all know that's a line. You can all see that coming up. Now, we are going to be centered near 2, right? So we want to be kind of near this point. So here's what I'm going to do. Let me start by changing the bounds on my y. So here's what I'm going to do. I'm going to make the bounds on my y 4.999 and up to 5.001. Now I'm also going to change the x a bit because we want to be closer to 2. So let me just for right now make it 1.9 to 2.1. Okay, so you notice that our graph looks like it's pretty much straight up and down. And that's not actually what this graph is, right? This is not a vertical line, but that's because of our scale. So let me change these to 1.99 and 2.01. And you're starting to see it slant, right? Well, I'm going to keep zooming in because right now the function in this interval does not all lie within this strip. This function runs outside of the strip, right? Like if you look down here, once we get really low, we get outside of the strip. And the same thing, right? So that down here we're exiting the screen and the same thing up there. Now, what I need to do is keep zooming in. I need to go to a smaller strip of y's, or sorry, strip of x's to see if we can get within there. Oops. So let's do that. Let's change this then to 1.99. And we'll go to 2.01. Right, so that's not quite good enough. So let's add in some more zeros. So go to 2.001, and this one will go 1.999. Now you notice that this is definitely flatter, and more of this graph is being shown in this strip. But what I really need to see is I need to see this part right here never dip below this line. And the same thing up above. I know you can't see it behind this, but up here, I need to make sure that it never goes above the top line. Okay, well, let's zoom in one more spot. So let's go to 1.999. Okay, now this would be a sufficient delta. Because notice now on the entirety of this horizontal bit, from here all the way over there, we are not running out of the top and bottom of the screen. but this is actually a smaller delta than I actually need. I could make delta a little bit bigger, right? So here's what we'll do. Let's make that a little bit bigger by, say, dropping that 9 on the end. Oh, no, that's too far. Let's make it a 5. Okay, so if I make those just a little bit bigger, now you'll notice that I went too far. This is now running down below. It's not entirely within my strip. But if you look at this, you could even make a guess on that number. It's somewhere between 1.9996 and 1.9997. So let's actually change this to a 7. So then this one should be a 3, because I'm on the same step. And again, you can see that we just are barely fine, right? We're not actually running down below, which means I can make it still bigger yet. Well, if you go back and you look at the number that we found when we actually did it, this would have been with a whole bunch of 6s afterwards. And this one would have been with a bunch of 3s afterwards. We'll go ahead and call that good. So let me go ahead and turn this guy off. And now you can see that we are just staying within this strip. It's coming down, just hitting the corner. So that's how you can do this graphically. I'm not a huge fan of doing it graphically because you have to do a lot of guessing and finding the zooming. It has to be just perfect. But that at least is how you can do this looking at a graph. All right, so questions on that one before we go and look at one of the other problems? All right, hearing none and seeing none. Let me go ahead and get some points though. What does it say? Within 3 decimal places? Okay, well it was 0.00033333333. Yay! All right, I got my point. So let's go look at number 9. So number 9, same idea, but this one we're not graphically doing it. This one we're going to just do it. All right? And so the function we're looking at is x squared plus x as we're going to 2, and they told us that the value is 6. And then they say choose delta be the minimum of epsilon over m, comma 1, and determine m. So I don't remember if you, I don't know if you remember seeing this, but we did one very similar to this in class. But let me go ahead and go to a whiteboard and we will go take a look at it. All right, so let me just go ahead and clear this real quick. All right. So let's see if we can do this guy. All right, so again, remember what we're going to do. We're going to do absolute value of f of x minus L is less than epsilon. And we want it to look like absolute value of x minus A is less than delta. So let's put in all the different things we know. So f of x is x squared plus x. The limit we saw was 6. So that's going to be less than epsilon. And we want this to look like the absolute value of x minus 2 is less than delta. All right, so the trick with this one is we want to factor it. Because this thing will factor to x plus 3 times x minus 2. Which then means if I divide that out, gives me epsilon over x plus 3. But now here's the problem. The delta should be what's on the other side here. But unfortunately, that thing has an x in it. And that's no good. So does anybody remember the trick we played, how we got rid of that x? Okay, that makes me think, no, we don't remember that. So what we did was we basically said this, okay, if x is near 2, right? We know that x is supposed to be near 2. Then I know that x is actually going to be between, say, 1 and 3. And do you remember in that homework problem it said, you know, the minimum of epsilon over m, comma 1? It was that comma 1 that told me to go between 1 and 3, because that's telling me how far to go, 1 step away. But I know that x is between 1 and 3, so I know that x plus 3 is going to be somewhere between 6 and 4. So then I know that epsilon of x plus 3, this thing that we were looking at right here, that's going to be somewhere between epsilon over 4 and epsilon over 6. So notice that these inequalities are the reverse of this one, because when you divide by a bigger number, you actually get something smaller. And with our search for deltas, we always go small. So we're going to take the smaller value, which is epsilon over 6. So what I know then is my delta is going to be the minimum of 1 or epsilon over 6. So the epsilon over 6 came from this, and the 1 came from specifying that my interval was 1 to 3. So it's definitely kind of a weird, quirky little thing, but it's something that we always have to do if there are x's that show up on this side once we get ourselves set up for just the x minus a piece. Now, choosing 1 was completely arbitrary. I could have gone a half, so I could have been x's between 1.5 and 2.5. Done exactly the same thing. I would have gotten a different number for below my epsilon, but then my minimum would have been 1/2, comma, epsilon over whatever it happened to be. But again, the problem itself suggested that I wanted to use 1 because it actually said so. All right, so is that better for that one? And again, your numbers might be a little bit different depending upon your specific function and all that, but it's this kind of process. All right, so not seeing any questions, not hearing any questions. Go ahead and go look at the last one then. And I think the issue with this last one is figuring out what each piece technically is. So let's go look at that. Actually, while I'm here, oh, never mind. Okay. So it says a machinist is required to manufacture a circular metal disc with area 905 square centimeters. There you go. Here your answers in exact form. Do not write as decimal approximation. So what radius x produces such a disc? All right, so let's think about this. We're looking at an area of a circular metal disc. So area of a circle is pi r squared. So in order to answer this first question, we're going to take pi r squared and set it equal to 905. So let me go back to a whiteboard here. Clear all that old stuff. Okay, so we know that the radius pi x squared has to equal 905. So x is going to be the square root of 905 over pi. And again, it asks us to put in exact values. So that's the exact value I'm going to put in. Okay, so then B, right, if the machinist is allowed an error tolerance of plus or minus 5 square centimeters, how close to the ideal radius must the machinist control the radius? Okay, well, I think you know what to do there, right? So now we're going to say our area can be 905 plus or minus 5 centimeters. So that means the pi x squared can be between 910 and 900. Right? And we can go ahead and solve this for x, right? Get some bounds for x. Let me just do it here. Okay, so we know that our radius has to be between those. And so I think the original question was, how close to the actual radius do we need to be? And so if it's how close to the actual radius we need to be, that's going to be the difference in these. Right? So how close? Well, that's going to be either this one. We're taking our now bigger radius from overestimating minus what it actually should be, or the actual one minus the smaller one. And we're going to choose the smallest, because these two numbers aren't going to be the same. But we're going to take the smallest one because that's how close we have to be. If we choose the bigger one and we say, well, we need to be within that distance, we might actually overshoot the smaller one. Okay, so calculate these two and you choose the smallest. All right, so now the question is, how does this relate to limits? Well, remember what limits are. We've got these two inequalities, which that should be a 2. 2. Excuse me. All right. So let's just think about what this is saying. Remember, epsilon was how close we have to be to the actual value. So in this case, the actual value, that is our area. So that's going to be our L. So what's going to be our epsilon? Remember what epsilon is how close we want to be to the actual value. So in this case, what's going to be our epsilon? All right, thanks, Aris. It's going to be 5. It's this guy right here. Right, because we're plus or minus 5. So there's our L and there's our epsilon. So then our F, the function that we're looking at, is pi x squared. And so this statement right here, where we got the pi x squared equals 905 plus or minus 5, that's exactly the f of x minus L is less than epsilon. Okay, so then what's our A? Well, A is an x value that we're plugging in. And it's the x value we plug in to get our limit. And so that's this guy. That right there is our A. And so then delta, remember delta is how far away can we be from that A? And that's this. So whatever we calculate is the smaller of these is our delta. Now, I guarantee you no machinist in the world is going to be thinking like this when they're, constructing their circular disc for whomever that they're manufacturing it. However, you can see that this really is the same idea if we really break it down. All right, so is that better for that one? Does that make a little more sense? He says, hopefully.
Yeah, no.
Yeah, better? Okay. All right, well then I'm going to go ahead and stop sharing here. Any other homework questions before I hop up to the board and we continue our discussion of derivatives? Okay, so today is actually going to be a good day. You are going to like today, or you're going to definitely like being at the end of today, because today is when we're going to develop all the rules for derivatives so that we can do this much faster and much easier, and we never have to worry about that limit definition again, except for like on an exam or something, right? We're not going to use that anymore after today, other than when we decide to prove more rules as we come. So basically, we're going to use that limit definition to prove the rules that we're then going to use. Real quick, Susanna just popped in with a question. Do I have an exam study guide for the week? The answer is no. I don't do exam study guides. The study guide is what we've talked about. We'll talk more about the exam on Wednesday, but let's just get this out of the way. It's going to cover everything up to what we talked about last Friday. So everything before the derivative rules, which I think is section 2.3. I'm not entirely certain. I'll be able to give you that number in a bit. But yeah, no study guide. You know what you need to do. All right, so let me go ahead and jump over to the whiteboard. I'll see you guys in just 1 second. All right, so as I was moving over here, I went ahead and looked into the book. I was off by a chapter. So what we're talking about today is 3.3. So the exam is going to cover up through 3.2. Right? All right, so today, here's what we're going to do. We are going to develop a whole bunch of differentiation rules. And once we get these, once we do these differentiation rules, we're never going to have to use the limit definition again, right? We're just going to use it today, bang these suckers out. All right, so I'm going to go ahead and just dive in, but before we do that, let me remind you the definition of the derivative, because we are going to be using this a lot. It's the limit as h goes to 0 of f of x plus h minus f of x divided by h. All right, so remember how that works. So h is just the step from our point to the next point. And this is just the difference in the y values divided by that horizontal step. And then we try to make that horizontal step infinitely small. And that brings us from a secant line to a tangent line. All right, so the first one we're going to do is we're going to look at a constant function. So when I write here f of x equals c, it's a constant. Okay, so this would be f of x equals 2, f of x equals 17, whatever. So the question is, what is that limit actually equal. All right, well, let's do it. Let's look at this function and put it into the definition of the derivative. All right, so we set this thing up. We're going to have f prime of x equals the limit as h goes to 0 of c minus c over h. Okay, so the reason that those are both c is that a constant function, no matter what you plug in, always gives you the same amount. So we're going to get c either way. So I'm literally just going to plug those in. Now, c minus c, of course, is 0. So we get 0 over h. And 0 divided by anything that's not 0 is 0. So this is going to be the limit as h goes to 0 of 0. Now, sometimes people here stop me and say, but wait a minute, we're dividing by 0, right? You get 0 over 0, which would suggest doing some algebra or something. But we're not dividing by 0. Remember, this idea with this limit is we're getting as close to 0 as we want, but it's not equal to 0. So this is totally legit. And so then 0, it doesn't matter what happens to h, just ends up being 0. All right, well, there you go. We just proved that any constant function, doesn't matter what constant function it is, its derivative is going to equal 0. Yay. All right, now, this is one where we didn't really need to do the calculus, if you think about it a little bit. Think about what the graph of a constant function looks like. All right, so here are our coordinate axes, and then a constant function is just a horizontal line. And if you were to take a tangent line to that line, well, tangent lines to lines are the lines themselves. And you notice that its slope is always the same no matter where we are. And since it's horizontal, its slope is always 0. Yay. Okay, so constant functions, their derivative is 0. You're going to like this. Constants are great, because when we differentiate, they just go away. All right, so there's your first differentiation rule. Okay, now let's bump this up a notch. And let's look at line. So let's say we've got a linear function. F of x equals mx plus b. Now, I'm not going to bother using the definition. I'm going to think about this for a second, kind of like we did here. All right, so instead of a constant function, let's go for a line that's not a constant function, something like this. So again, remember what the derivative is doing. It's finding the rate of change, the instantaneous rate of change, which is the slope of the tangent line. So if I have a tangent line to this line, the tangent line is that line, and notice that its slope never changes. What is its slope?
Rise over run.
So it's the rise over run, or if we have the formula, like Mariola just said, it's m. It's that slope. So the derivative of this thing is equal to m. So if you ever have a linear function, its derivative is always m. It's always the slope, because the derivative is the slope. Okay, now you can easily prove this using the definition. You'll see that once you simplify everything down, take your limit, you do get m. But I'm not going to bother. We're just going to use our brain, right? Okay, so yay, that's for line. Now, I'm pretty sure that we did do x squared. We saw its derivative was 2x. But here's what we're going to do. We're going to simplify down even further and just go, what if we have x to a power? So this will work for x squared, x cubed, x to the fourth, so on and so forth. Okay, now this one I do want to prove. I want to show you what it actually equals. And I know that when we started doing a few of these last time, people started seeing a pattern, had something to do with the exponents. And let me show you what happens here. So we're going to go ahead and just jump to the definition of this. So we're going to have f prime of x is equal to the limit as h goes to 0 of x plus h to the n minus x to the n over h. So it's the same rule every time, right? It's the same process every time, same form. We just need to apply it to this function. All right, now I'm going to use the binomial expansion theorem on this. So you're going to get x to the n plus n, x to the n minus 1 times h plus, I'm going to go a little bit lower so that the glare doesn't cover this up. So x to the n plus n, x to the n minus 1 times h plus n times n minus 1 over 2 times x to the n minus 2h squared plus, that's just what the next one happens to be. And then we keep playing around with this until eventually we get to a n x h to the n minus 1 plus h to the n minus x to the n. So again, all of this was the x plus h to the n using the binomial expansion theorem. That's something I hinted at before, right? Pascal's triangle, whatnot. So go back and look at that if you're a little bit unsure of it, but you can trust me that this is what it's going to look like. This dot, dot, dot means there's a whole bunch of terms. How many terms kind of depends on what n is, but they're all there. All right, but now we're going to do some simplifying. So I've got an x to the n minus an x to the n, so those cancel. All of the remaining terms have an h. They've got at least one h, so I'm going to divide that out as well. So this h on the bottom is going to cancel. With one of the h's in each of those terms. And now I'm going to take my limit as h goes to 0. So notice this first term does not have an h. So it's just n times x to the n minus 1. The next term has an h. It's got h to the first. So when we plug in 0, that goes away. The next one's going to have an h squared. Plug in 0, that goes away. Then an h cubed, h to the fourth, and so on. All of the rest of them have h's, which when we plug in 0, makes them go away. So what we're left with is just n times x to the n minus 1. And that, ladies and gentlemen, is what we call the power rule. So this one's got a name. It's called the power rule. But we now have differentiated every power of x. I don't think you see the like, I was just about to say, see the power in that. I don't think you quite get how huge that is. Because now, x to any power, I don't even have to think anymore. I have a rule, I can just use it. Right? So check this out. Here's how fast this can be. Let's say we've got f of x equals x to the 5th. All right, well, f prime of x, here's what we do. That power comes out front as a multiple, so 5, and then we decrease the exponent by 1, 5x to the 4th. That's the derivative of x to the 5th. All right, well, let's go bigger. Let's say we've got g of x equals x to the 37. Okay, well, the rule says bring that power out front, decrease that power by 1. So the derivative of x to the 37 is 37x to the 36. Fast. Here you go, here's one more. What if we have h of x equals x to the 500? Now, 5001. All right, so h prime of x is going to be 5001x, and then I decrease the exponent by 1. So I get 5001x to the 5,000. So any power whatsoever, we can now differentiate. So maybe you're seeing the beauty in this. We use the limit definition one time, and now any of these things we can tackle. Well, if you think this is strong, you ain't seen nothing yet. Because check this out. Let me give you another one here. Let's say we've got f of x equals the square root of x. Now, this is another one I think we already proved. But watch what we can do. Radicals, those are the same as fractional exponents. So the square root of x is the same as x to the 1/2. Hey, wait a minute. That's a power. We can use the power rule. So the derivative of this thing is going to be 1/2. We bring that exponent out front. And we're going to get x to the 1/2 minus 1. Well, subtracting 1 from 1/2 gives us negative 1/2. So f prime of x is 1/2 x to the minus 1/2, which is the same as 1 over 2x to the 1/2. Negative powers, we drop them down to the denominator. And I can even turn that back into a square root. And so we see that the derivative of the square root of x is 1 over 2 times the square root of x. And go back to last week some point when we actually proved the derivative of the square root of x, and you'll see that we did get 1 over 2 root x, but it took way longer when we used that limit definition. We ended up having to rationalize and do all that kind of stuff. This is super fast because we did it one time. We took care of every power, every possible power. So it doesn't include just integer powers. They can be fractional powers. So any kind of a root, we now have a way of dealing with them. Okay, that's still not everything. Let me show you another one that you might not expect that this works for. How about this guy? What if I told you, let's find the derivative of g of x equals 1 over x. So that's another function I know that we've done. You can go back and look at your notes and you can find a derivative. But let me show you how fast this is if we think of it as a power. So what power can we put on x to get 1 over x? All right, cool, negative 1. All right, so we got a couple of you throwing out there that this is negative 1. So yeah, this is the same as x to the minus 1. Well, now that we know that, or see that, this is really fast. Bring the exponent out front. and then decrease the exponent by 1. So -1, if I subtract 1, gives me -2. And so I can rewrite that as -1 over x squared. So the derivative of 1 over x is -1 over x squared. And that's another one that I know that we did. So you can go back and you can look at your notes. But you'll see how it took us way longer because we had to do all kinds of fractional stuff inside that limit definition, where this power rule is quick, super, super fast. Okay, so remember this one. Remember the power rule. It is going to be your friend for sure. You're going to like things that are just x to the n because they're really fast and easy to differentiate. All right, so there you go. There's the power rule. All right, now the next one I want to do is another kind of generic guy, which is constant multiple rule. Meaning, what if we have g of x equals c times f of x? And we'll leave a spot here for g prime. And so this one I'm going to call, I don't know that this is actually what it's called, but I'm going to call it the constant multiple rule. Right? So it's the rule when we're multiplying by a constant. See, I can name things like a mathematician, no problem. All right, so constant multiple rule. So we've just got some sort of function we're multiplying by c. So this would be like 5 square roots of x, 2x cubed, -3 sine of x, things like that. Okay, so just some constant times a function that we already know. So the question is, what happens with its derivative? Well, let's go back to the definition and let's see what happens. All right, so we're looking at g prime. So g prime of x is going to be the limit as h goes to 0 of g of x plus h minus g of x over h. So let's put in our function. Right? G of x is just c times f of x. So this is going to be c times f of x plus h minus c times f of x, all divided by h. All right, so again, just definition. But notice on top there, both of those things have a c, so I can factor that out. The limit is h goes to 0 of c times f of x plus h minus f of x. And since that c has nothing to do with the h, we can actually pull it outside of the limit. So I'm going to go ahead and do that. Back when we were talking about limits, we had all kinds of limit laws, limit rules. Well, that was one of them, that constant multiples come in and out. So you might remember that. If not, again, you can go back and look at your notes, but we definitely did that. All right, so we're here, and it's about this point you go, yay, so what? Well, the so what is, look at this limit. We know what that is. That's just f prime, right? Look back at the top here. That's just the definition of f prime. So this is c times f prime of x. And that there is the constant multiple rule. If you have a function that's being multiplied by a constant and you differentiate, that constant just stays there. I'll say it goes along for the ride. Okay, it just carries down And all we have to do is differentiate the other function. So constants by themselves just went away, but constants that are being multiplied stick around. All right, so let me show you how this works. Let's take some functions with constant multiples and see what we get. All right, so let's run over here. Let's say we've got f of x equals 4x cubed. So we're going to differentiate that. Okay, so that 4 is a constant multiple. It's just going to stay there. And then we need to differentiate x cubed. Well, x cubed, we know that that's a power rule. So we bring that multiple out front, 3. And then we decrease the exponent by 1. So that becomes x squared. So we got 4 times 3x squared. Multiplying that all together gets us 12x squared. So the derivative of 4x cubed is 12x squared. There you go. We're done. Here's another one. Let's say we've got f of x equals 6 over x to the 4th. So this is one where we have to get a little sneaky. The x to the 4th, recognize that that's a x to the negative 4. But now that we've got that, here comes our derivative. The 6 is a constant multiple, so it just stays there. X to the minus 4, we bring the minus 4 out front as a multiple. And then we decrease the exponent by 1. So negative 4 minus 1 is negative 5. So we get negative 24 x to the minus 5, which is the same as negative 24 over x to the 5th. So that's the derivative of 6 over x to the 4th. And this is way faster than trying to do the limit definition. And that's because we already did the limit definition one time, knocked it out. Okay, so constant multiples are a piece of cake. Super easy to use. Don't really have to do anything. We just keep that constant and roll with it. All right, so let's keep going. The next rule is going to be this one. What if we've got two functions that we're adding? Okay, so we're going to say that, let's say that h of x is equal to f of x plus g of x. Then the question is, what does the derivative of that look like? So if we have a sum of functions, right, x plus root x, sine x plus cosine x, whatever, we've got two functions that are being added. What happens when we differentiate? All right, well, we're going to do what we always do, which is just start with the definition. So h prime of x, it's going to be the limit as h goes to 0 of h of x plus c minus h of x. Yeah, I need to change this. Instead of a h on the bottom, let's make that a t. Make it a t. I had to change its name because h is the name of my function. So now t, that's just that gap, and we're shrinking that gap. Okay, just change the name. It doesn't really do anything different. All right. Well, what's t? So now let's see what happens here. So this is going to be the limit as t goes to 0 of f of x plus t plus g of x plus t minus f of x minus g of x all over t. So f of x plus t plus g of x plus t minus f of x plus g of x. All right, so what I'm going to do is I'm going to split this apart. I'm going to break this into two pieces. I'm going to get all the pieces that have f together, and then all the ones that have g together. So we're going to get f of x plus t minus f of x. So that was the two pieces with f. And then the two pieces with g. We're going to have g of x plus t minus g of x. So don't forget to distribute that minus sign. So both of those are negative. All right, now, these two limits, if you look at them individually, this first one, that's just the derivative of f. The second one is the derivative of g. And so what we're left with is f prime of x plus g prime of x. And so we can go ahead and put this up into our rule. Okay, so this is the sum rule. So if you have two functions that you're adding, and you take the derivative, you can differentiate each one of them separately, and then add them together. All right, so this was from addition. It turns out that if you do subtraction, the exact same thing falls out. I'm not going to bore you with that, but what I am going to do is up in our rules, you notice I'm going to write this as plus or minus. So if we have f plus or minus g, the derivative is going to be f prime plus or minus g prime. All right, so that's the sum and difference rule. So adding or subtracting, you just do each one separately. All right, so basically all this means is if you got this huge string of things, instead of tackling them all at once, do them each individually and then piece them together as you need. All right, well, here is the power of this rule. Basically, between the one that we just did, number 5, and number 4, the constant multiple rule, and number 3, the power rule, you can now do any polynomial. And you can do any polynomial rather quickly. So check this out. Let's say that we've got f of x equals 3x to the 5th minus 2x to the 4th plus 6x minus 5. So some polynomial. Here's how we get the derivative very quickly. We start by breaking it into 4 pieces. We're going to look at each term individually. We're going to take their derivatives and then add or subtract as we had in the original function. All right, so here we go. The first one, 3x to the 5th. The 3 is a constant multiple. X to the 5th is going to give me 5x to the 4th. So that's 3 times 5x to the 4th. Now I'm going to put a minus, and that minus It's just carrying down, because when I have subtraction of functions, I differentiate each one separately and subtract. Okay, so the 2x to the fourth. 2 is a constant multiple. X to the fourth gives me a 4x cubed by the power rule. And then I put a plus. All right, so we get to the 6x. The 6 is a constant multiple. Let's think about x to the first. That's going to give me 1 times x to the 0. So just real quick, in case you didn't catch that, x, think of that as x to the first power. So the power rule says bring that exponent out front as a multiple and decrease the exponent by 1. All right, then I'm going to put a minus, because that's what we were doing here, right? We were subtracting. And now I differentiate 5. Well, 5 is a constant function, so it just goes to 0. So this polynomial had 4 pieces to it. So my derivative has 4 pieces to it. And again, they're being added and subtracted as before. All right, well, let's just see what this gives us then. We get 15x to the fourth minus 8x cubed. We're going to get plus 6 x to the 0. So let me just remind you that if you raise something to the 0 power, you get 1. So x to the 0 is just 1. So we get 6 times 1, which is 6. And then we get minus 0. Okay, well, we'll just let that go. All right, so there is your derivative of 3x to the fifth minus 2x to the fourth plus 6x minus 5. It's 15x to the fourth minus 8x cubed plus 6. All right, so this was for a polynomial, but you really can do the same process anytime you're adding or subtracting a whole bunch of functions together. Split it apart, do each one separately. All right, so again, we did the limit definition one time, and now we can just dive right in. So you're going to actually like polynomials. You're going to wish that you could differentiate those all day long, because they're super fast, super easy. All right, so before we tackle the next couple of rules, any questions up to this point? I know I'm throwing a ton at you, but notice it's the same thing every time. I start with the definition of the derivative with the limit. I do it generically, and I get some rule. Basically, the whole point is, now that we've done it once, you never have to do it again, and we can do this quickly, right? We can be fast. Okay, so seeing no questions, hearing no questions, let's move on to the next guy. And the next one, I guess this is going to be number 6. Now that we've added and subtracted, what about when we multiply? So we're going to have h of x equals f of x times g of x. And the question is, what does h prime equal? I think you can kind of see the progression here, right? We're doing add and subtract, so now we're going to do multiply. After we get done with multiply, we're going to do divide. After we do divide, we're going to go to composition. All right, we're just going to keep doing these operations, and we're just going to see what we end up getting. All right, so this one, of course, is going to be called the product rule. So just we'll go ahead and put the name here. So let's see if we can develop the product rule. What is this thing going to actually look like? All right, well, let's just start with the definition. So we're going to get h prime of x is going to be the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x, all divided by h. Right, because it's a product, f times g, so go ahead and just put those in there. All right. So now, how do we deal with this? So you may remember with the add and subtract, I just kind of split it. I took all of the things that had the f's and I put them together, and then all the things that had g's and put them together. But unfortunately, I can't do that here. Just it's not going to work out because the f's and the g's are being multiplied to each other. All right, so here's what we're going to do. We're going to use a miracle step. And I think I've told you about miracle steps, right? Miracle steps are the, what do we do? Let's just do this. Why? Because it works. Okay, I get miraculously, right? The math god smiled upon us and figured out that's what we needed to do. Well, that's basically what happened with this one. Somebody, I don't know who it was that actually proved the product rule, but when they were fiddling around with it, they figured out this was the next step. So it's going to be a miracle, but there's a reason that it works. And so here's what we're going to do. I'm going to pull one of the oldest tricks in the math book, which is I'm going to add 0. But I'm going to add a special form of 0. Just go with me here. All right. I'm going to put in here a minus g of x plus h times f of x. But in order to counter that, I'm going to add exactly the same thing. So those two terms in red, those things cancel each other out. They're exactly the same thing, just one's plus and one's minus. So they go. So in essence, I just added 0. All right, well, adding 0 doesn't change anything, but I definitely have a couple more terms. All right, so that's our miracle. Miraculously, this worked. So here's what I'm going to do now. I'm going to split this. I'm going to split it into 2. So we're going to get the limit as h goes to 0 of, and I'm going to literally just take the first 2 and the second 2. So I've got f of x plus h times g of x plus h minus g of x plus h times f of x. And then I'm going to add to that g of x plus h f of x minus f of x g of x divided by h. All right, so looking at the first set, this first fraction, notice that there is a common factor on top. There's a g of x plus h. Let me factor that out. So I've got the limit as h goes to 0 of g of x plus h times f of x plus h minus f of x over h. So that was this piece. With the second piece, I also have something that I can factor out. I've got an f of x. So let's factor that thing out. All right, so I'm just going to run over here. I'm going to get f of x times g of x plus h minus g of x all over h. So just a little bit of algebra. But I did this on purpose because now I'm ready to take my limit. Look at those pieces with the fractions. Those, when I take those limits, are just going to give me the respective derivatives. So here's what we end up getting. All right, as h goes to 0, this first piece, g of x plus h becomes g of x. This fraction becomes f prime of x. On the second piece, f of x is still just f of x. But that fraction in the second piece, that's g prime. And so that is our product rule. Ugh. All right, it's definitely not pretty. But let me go ahead and write it here. I'm going to change the order just slightly. Since it's multiplication, the order doesn't matter. I like to start it with f prime of g, or f prime of x times g of x. All right, so now is where we get a little bit unhappy. Everything was awesome so far, right? Like we do it, we get the rules made sense, super nice. This one now, the rule doesn't make sense. It seems like we should just take the two functions, take their derivatives and multiply them together, right? I mean, it seems natural that that's how it should work, but it doesn't. It doesn't work that way. It's the derivative of one times the other, plus the derivative of the other one times the first. Okay, so we really need to think of these as the two functions being multiplied together. We're going to differentiate one and multiply by the other one, and then vice versa. Okay, but it's the product rule. This is how it works. We know it works this way because we proved it. We went through the steps and saw that it must be this way because math suggests that it must be. Okay, so let me show you how this works. Let's actually take some functions and I'll show you how they work. All right, so for example, let's say we've got, let's say we got y equals x sine x. So you can definitely see the multiplication, right? You've got x and you've got sine of x. So if we were to break this down, kind of like what we have written up above, here are the two functions. So f of x is x, and g of x is sine of x. And I am going to do this every time we do a product rule, at least early on for quite some time. I'm going to write it out as the two different functions that are being multiplied just to help you see it. Plus, it will help us kind of organize to get our derivatives. All right, so we've got x times sine of x. All right, now think about what we need. If you look at this formula, we need both derivatives. So once I have this, I like to go ahead and find both derivatives. All right, so what's the derivative of x? So you can actually tackle this in one of two ways. You can think of it as a power, x to the first, and use power rule. Or you can think of it as a line and just tell me the slope of that line. That's what I would do. All right, there we go. Thanks, Mariola. It's 1. So the derivative of x is 1. 1x to the 0 from the power rule, or just using the slope. Okay, so now, question for class. Do you remember the derivative of sine? Because we did that before, and this is one of those that you should know. All right, so if you don't have it yet. So Susanna has just put up here cosine of x. Good. The derivative of sine is cosine of x. So we proved that. We had to use the sum of angles identity. Maybe you guys remember it was kind of ugly looking. But we were able to actually get that the derivative of sine is cosine. Okay, so now let's use the product rule. So the product rule says we're going to take the derivative of f times g. All right, so here's the derivative of f, is 1. And we're going to multiply it to g. So we're going to get 1 times sine of x. And then we're going to add to that f times the derivative of g. Okay, well, here was f. And there was the derivative of g. So we're going to get x times cosine of x. All right, so the derivative of x sine of x is sine of x plus x cosine of x. And there it is. There's the derivative of that function. And again, I promise you, way faster, crazy way faster than trying to do the limit definition. But that's because we already did the limit definition one time to care about. All right, let's do another one. Let's do y equals square root of x times 4x squared minus 2x plus 3. Now let's make that a cube root. We do square roots all the time. Let's make one of these a cube. All right, so let's think about what the functions are that we're multiplying together. We've got f of x is the cube root of x, and g of x is 4x squared minus 2x plus 3. All right. So now what we need is the derivative of each one of them. So my process when I do this, I start with the two functions, and then I jump right to getting their derivatives. So I'm going to write f prime of x equals and g prime of x equals. I'm going to find those. So this one, think of that cube root as x to the 1/3. It's a fractional power. So we can go ahead and use a power rule. So that 1/3 comes out front as a multiple. I decrease that by 1. So 1/3 minus 1 is minus 2/3. So that's 1/3 x to the minus 2/3. The other one, since it's a polynomial, I'm going to do each piece separately and add them together. So 4x squared, we get 4 times 2x. Then I'm going to subtract 2 times the derivative of x, which was just 1, plus the derivative of 3, which is 0. So that's 8x minus 2. All right, so let's put it together. Here is your derivative. So y prime equals, I want f prime times g. So I'm going to take 1/3 x to the minus 2/3 times 4x squared minus 2x plus 3. And then I'm going to add to that, I'm going to write it down below because I don't have enough space. But I'm going to add to that f times g prime. So x to the 1/3 times 8x minus 2. So just like before, I took f prime times g, and then I took f times g prime. All right, now I'm going to leave it like this. A lot of times people ask me, do we need to simplify this? And my answer to that is usually, it depends on what the situation is, what we're trying to do. For me, I want to see that you know how to do the product rule, so getting here is good enough. If we then wanted to use that derivative for something else, which we will later, that's where we're going to want to do the algebra. We're going to want to simplify and do all that good stuff. But for right now, we can just leave it like this. Okay. All right, so there's another example of the product rule. So I don't know if you noticed this, but I always set it up the same way. Because I always set it up the same way, it's pretty easy to remember the product rule. So remember, I did f and g, I wrote their derivatives, and then I just have to multiply a derivative times something else. Well, here's how I remember it. I just multiply across. Think about like a cross product. If you set it up the way that I set it up, you just have to multiply cross product. And again, it doesn't matter which one comes first since it's addition. Addition's commutative. You can just slap them in however you want. All right, but you're going to see that I always do this. I always set it up f times g. So I've got f prime times g prime, which then means I can just do a little cross product-y kind of thing. All right, so how do we feel about the product rule? Are you going to be able to do it on your own? With some practice, at least? I hope. All right, well, there's product rule. Kind of nice. It always works exactly the same way. It's not intuitive. It's not take the derivative of each and multiply them together. All right, so the next one on our list then is going to be the quotient rule. And the quotient rule is exactly what it sounds like. Now instead of having f times g, it's going to be, what do we get when we do f divided by g? All right, but I'm going to be nice. I'm going to have a little pity on you. I'm not going to derive this one. I'm not going to make you watch where it comes from. You can look at it in the book. You can find it online. If you're curious about it, come talk to me in office hour or something. I'll be happy to explain it. But I think overall, most of you, at least at this point of today, are probably like, yeah, I'm done. I don't want to see any more limits. I don't want to evaluate any of this stuff anymore. I'm done. And that's cool. I get it, because I've been throwing a ton at you. But we need to at least get the quotient rule today, because otherwise I don't want to leave that one hanging, because they just kind of all go together. All right, so I'm just going to give it to you without proof. Again, I will show that proof to you individually if you'd like sometime. But here's how this one works. Now, just like with the product rule, we need the derivatives of both of them. We're going to get a fraction here. And what you're going to see on the top of the fraction looks a lot like the product rule. So notice that the only difference here between what I've written on the top of this fraction and the product rule was that this is now a subtraction instead of an addition. Probably not a huge stretch in your mind that that would happen, since dividing is really multiplying, right? It's like backwards multiplication. Well, then that fact that that led to subtraction instead of addition, kind of go, yeah, that makes sense. Okay, so the top totally makes sense. The bottom of this thing, yeah, this doesn't make sense. It is. It's the original bottom squared. Of course. All right, but this is the quotient rule. So no matter what, when you have two things that are being divided, two functions are being divided, this is how you can set up their derivative. So let me walk you through a couple, and then I'm going to give you some tips for how to remember this formula. Okay, because this one's tricky. The product rule, you probably can get that one down pretty easily. Quotient rule might help if there's some ways to remember. So, and I will share that with you. But let me first show you some examples. So start. Let's say we've got y equals x over 3x minus 2. Kind of a typical butterfly function. Okay, so we're going to set it up the same way that we did last time. We need to know the derivatives of both of the functions. So let's list them out here. For this formula, f is the one on top. So we're going to have f of x equals x, and g of x equals 3x minus 2. So according to our formula, that's f and g. So I need both of their derivatives. So the derivative of x we've seen is 1. And the derivative of g, it might be easiest if we just recognize that g is a line. 3x minus 2, right? That's just a line. So its derivative is its slope, which is 3. But feel free to use the rules to figure out the derivative of that if you need. All right, so let's put this all together. So the derivative of this function, we start with the derivative of the top, which was 1. And we're going to multiply that times the bottom, right? So f prime times g. So we're going to get 1 times 3x minus 2. And then we're going to subtract f times g prime. So f was the top, g prime, that's the derivative of the bottom. So we're going to get minus x times 3. So that's those pieces. And then we divide by the bottom squared. So that's going to give us a 3, or sorry, a 3x minus 2 squared. Now this one I am going to simplify a little bit, just because I can. 3x minus 2 minus 3x just leaves me with a negative 2. So we get y prime is equal to negative 2 over 3x minus 2 squared. So that's the derivative of this function using the quotient rule. So start like before. Look at the two functions, find their derivatives, and then just put everything into the respective pieces in this formula. Right? Here are the two functions, x, 3x minus 2. Here are their derivatives. Go. All right. So there is that one. So let's do another example here. let's go with the square root of x. No. Let's do this. Let's do sine of x divide cosine of x. Yes, there are two functions. The top is sine, the bottom is cosine. So I need to differentiate both of those. Okay, well, we saw a sine not that long ago. Its derivative is cosine. And we developed the derivative of cosine last time, or maybe 2 times ago. Anybody remember what it was? And it's okay if you don't. All right, so Susanna just put in the chat negative sine, and that is correct. So there are derivatives, respectively. So now let's get our y prime. So y prime is going to equal, so remember what we do. We start with the derivative of the top one, so cosine times the bottom one. So I'm going to get cosine of x times cosine of x. Then I'm going to subtract the top one times the derivative of the bottom one. So that's those guys. So I'm going to get sine of x times minus sine of x. And then I'm going to divide that by the bottom squared. All right, and again, this one I'm going to simplify real fast, again, because I can. I'm going to get cosine squared plus sine squared, right? The two minus signs cancel. So cosine squared plus sine squared is 1. So we get 1 over cosine squared. So the derivative of sine over cosine is 1 over cosine squared. Again, from the quotient rule. All right, so that's how this works. It's, again, very procedural. It's the same thing every time. If you have division, same thing every time. Differentiate the top, differentiate the bottom, fire them into this formula. Okay, so let me share with you a couple ways of remembering this formula. Okay, so the first one is very non-mathematical. It's just a little rhyme that is useful for some people. It's horrible for me, but it works for a lot of people. So I'm going to share that with you. And then the second way I'm going to share this with you is a very Bruce way of remembering this. You'll understand when we get there. Okay, so first let me give you the little rhyme for remembering the quotient rule. Okay, so it's just a little phrase here, and it goes like this. Low D high minus high D low square the bottom and away you go. Okay, so low D high minus high D low, square the bottom, and away you go. All right, so you notice how this is very rhythmic. It's like a song. Low D high minus high D low, square the bottom, away you go. All right, so this is how this works. Low is the bottom function. High, that's the top function. Anytime you see a D, That's telling us to take a derivative. So if you look at the top here, it says low d high. So low, g of x, d high, f prime, minus high d low, high, f, d low, g. Square the bottom, g squared, and away you go. All right, so low d high minus high d low, square the bottom, away you go. So if that works for you, awesome, use it. Totally use it. My problem is I get it all mixed up. Like, is it low d high, high d low d high? Like it all gets kind of jumbled up in my mind. But that's not at all how I remember it. So here's how I remember it. First of all, the squaring the bottom, just, yeah, that happens. Right? Even in this part, in this little rhyme, the square the bottom part, I never forget. So I just square the bottom. But the question is, what about the top? How do we make sure that we arrange this properly in the top? Well, if you set it up the way that I set it up, you can never fail. First of all, recognize that it's always like the cross producty thing, right? Like I've even got them color coded over here. Like I got the blues together and I got the greens together. So that's like a cross product. Down here, I had the reds together and then the blacks together. Again, it's like a cross product. So you do the cross product thing. And then one of them needs to be positive and the other one needs to be negative, right? One of them is a positive term, the other is a negative term. So this is how this weird mind remembers it. When I do that cross product, I just drew two lines, right? There's the one that goes up, like across, and another one that comes down. So check this out. I'm chuckling because this is kind of sad and pathetic how I think about this. One of those has a positive slope, and one of them has a negative slope. The positive slope one is the piece that goes with the positive. The negative slope one goes with the negative. Yeah, I'm a nerd, no doubt about it. But it totally works for me. Totally works for me. So if that helps you, cool. If it doesn't, use the rhyme. The rhyme works for you, cool. If it doesn't, if neither of these do, figure out your own thing. All right, because these are the only ways that I've ever learned how to memorize it. So get it down, get the product and quotient rules down because they are going to be huge time savers. We're going to use them a lot, save ourselves time going forward because we don't have to do the limit definitions anymore. All right, well, we're out of time. In fact, I'm over time. I'm so sorry. I just realized that I'm a little over time. So where we are, where we're going to go. We still have one more rule we got to develop. What do we do when we have composition, right? Because that's another operation that we can do with functions. So we'll take care of that next time. And we'll just keep plugging along with this stuff. We'll keep developing more rules. And then once we kind of have all the rules, we'll start using them. We'll start seeing why do we care about the derivatives. So for those of you who are always waiting for that, for the, yeah, but who gives a shit, it's coming. I promise it's coming, but we got to get the rules down before we can kind of dive into them. Plus, I've already hinted a little bit at some of the things we use derivatives for, but they're incredibly useful for lots of other topics. Anyway, all right, so Wednesday, we're just going to keep plugging along. We will do some review for the exam on Wednesday, probably a good portion of our time. And we'll also go over the quiz at the start of class. So don't forget homeworks. There's a set of homeworks that are due tonight at midnight. So make sure you get in there and finish those off. But other than that, you guys have an awesome couple days, and I'll see everybody on Wednesday.
Is it Bruce?